For the last part of our lecture, we're going to introduce our next topic that's going to involve torsion. And I'm going to ask you to guess what that might be. Now, I can't hear you, I can't read your mind or anything, but if you give this a little bit of thought, you could probably suspect where this might be heading. And of course, that's going to be statically indeterminate torsion. Very, very similar to the axial bar, but I think it's a little bit easier, a little bit better. We'll even write that out. It is a bit better and easier. Why is that? It is easier for two reasons. First off, you've got some experience. You've already done the axial loaded bar problem. Secondly, there are only two types, not three. And that's what's attractive about this. Once again, we want to set this up and do it sort of by example and then give you a chance to practice that. The first kind that we'll study is going to be the fixed. The fixed bar in torsion. And it's going to have a format very similar to what we had earlier. So let's go ahead and just make one up. Something like this. And at this location, let's say that we've got 10 kip inches going to the right. And then let's put maybe at this segment 4 kip inches going to the left. We'll call this A, B, C, and D. Now in this example, we're going to go ahead and take B, C to be one material, and then A, B to be another. So almost always that's going to be called out in the problem statement. So we'll go ahead and say A, B, and we won't even worry about what type of material it is. Let's say that its outer diameter is 4 inches, and it's solid. And it's got a value of G of 10,000 KSI. From B to D, that is also just a single material. So that means that I'm applying this torque. Oops, I should have put a double arrow, my apologies. We have a torque at C that is going to be a value of 10. And so we'll say that this one is hollow. So let's say that the outer diameter is 2 inches and the inner diameter is 1 inch. So it's hollow, and it has a G value of 15,000 KSI. Now, as we know from our experience in dealing with for the axial bar, the primary unknowns in terms of statics are going to be the two reaction values. So what we're going to do is the same thing that we did earlier. I'm going to go ahead and write my reaction at the left-hand end, and I'm going to draw it to the left. So I'll call that R1. The other reaction isn't as important, but we might as well put them in the same direction. So we'll call that R2. Now, if we knew one or the other of those, then we would have the value of internal torque everywhere, and we would be very, very fast. So let's write this up. If we knew R1 or R2, obviously we can get one from the other, it would be very, very fast. We could apply T rho over J piecewise. We could apply TL over JG piecewise, and we would get our answer again very, very quickly. But we don't have those, so that is going to be our objective, is to find out what those values are going to be. Now, let me see if we can move this guy here. And our tools are the same. We still have the big three. And what are those? Well, remember the first one is going to be statics. That means that the deformed section under torsion has to be in equilibrium. But remember, for the fixed problem, there's two parts to that. That would be the global equilibrium statement, but more importantly are the internal values of the torque in terms of R1. So I'll say T in terms of the left reaction. You do not have to do it this way, but in my opinion, it's the fastest and it's the most systematic. So we have statics. The second is stress strain. But remember, for axial, that manifested itself as delta is PL over AE. That means that for us, it's going to appear as theta is equal to TL over JG for each segment. Because we're going to acknowledge that for this type of problem, the torque is not going to be the same. In fact, neither is J and possibly not G. So we're going to have to apply those piecewise or for each segment. The third of our big three is going to be compatibility, which means that the deformed geometry has to be geometrically consistent. That means that there can't be any gaps or voids and so on. So let's apply this. That was a little bit of an aside just to remind ourselves what the big three is, our three main tools. And so let's go ahead then and apply these things. So I'm going to give you a picture again of what that was at the start. So to get the internal values of torque, first off, we could draw the global statement of equilibrium for this entire segment. Instead, let's put some lengths in here. Let's say that this is 4 inches. Let's give this 8 inches and 6 inches. So the three segments have those particular lengths. All right, so remember what our job is when we do the statics. We need to ask ourselves, okay, how many segments are there going to be? How many individual pieces do I need to apply TL over JG? And we can see for this one, there's 3. There's a break in the value of J between these two. There's a break in the value of J and G actually between those two. And the value of the internal torque is going to change between those two because of the appearance of that point torque of 10 kip-inches. So clearly we need 3 segments. That means we're going to have to make 3 cuts. Here's number 1. Cut number 2 goes to the segment BC. Cut number 3 goes between C and D. So those are the values then that we have to make for, oops, sorry about that, for this particular system. Okay, so let's go ahead and do the statics part. And for this, we'll make our first cut. So again, there's the squiggly line where I've made cut number 1. And there is our reaction that's assumed going this way. So the nice thing about drawing the reaction going to the left is that T1, or T of AB, however you want to call it. But this time we'll use this nomenclature because it's the first of 3. And that's just going to be equal to R1. Then our second cut, again, we include the entire segment of AB, and then we go into B and C. So we have R1. And here is our torque of 4 going to the left, like so. And then there is our internal torque of torque 2. Or if you want, you could call it the torque between B and C. This is something that I'm not going to be picky about. As long as you show me that you understand what the difference between those two, you understand what those are, that's fine. So this one then, we would write the torque in BC, which is going to the right. We just add the ones to the left. So that's going to be R1 plus 4. So notice the torque in segment 1, or AB, is going to be just R1. The second torque, torque 2, is going to be R1 plus 4. They're both in terms of R1. Then the last segment that we make is going to be this element. So we have 4 going to the left, and right here we have 10 going to the right. And then there is R1. So now we have our third torque, which is going to be the torque between C and D. And that's going to be actually R1 plus 4 minus 10. So that would be somehow to be R1 minus 6. So notice, now we have the values at the end of this step. We have the values of the internal torques all in terms of R1. Let's write that up. We have all internal torque in terms of 1 unknown, and that's R1. exclamation point. That's kind of a big deal. So we're highlighting that just to make sure you recognize that. R2 is nowhere to be seen. Now, if we wanted to, we could go ahead and write out global equilibrium. How is that going to appear? So the global equilibrium statement would be R1 plus R2 plus 4 minus 10 is equal to 0. We could simplify that, but that would allow us to find R2 in terms of R1 if we needed it. But we may not ever really use that. So may not use. In fact, we could get away with the whole problem in avoiding the use of R2. We could certainly get it, though. It's important to know what that value of the reaction is going to be. Now, next, so we've used our first tool, which is statics. The second part then is going to be stress strain. And the way that that appears in torsion problems is theta is equal to TL over JG. So now we have 3 segments. We need 1 per segment. It's very important. So we can say the twist in bar 1, or you could say the theta of B relative to A. Any of those are okay. So theta 1, which really means the twist, the angle of twist of B relative to A. And that's going to be, I'll write it like this, TL over JG for bar number 1. Our theta 2, that means the twist in bar 2. And what that means is theta of C, not relative to A now, relative to the left-hand end of the bar. And that's going to be the TL over JG for the second segment. That means the segment that goes from B to C. And then finally the theta 3, which is theta of D relative to C. And that's going to be the TL over JG of bar number 3. So when we come back for the next lecture, we'll actually do this, but we'll substitute in our known values that we have, and then ask ourselves, how are we going to impose compatibility for this particular system? But we'll go ahead and close it out since we're close right now. See you next time.